Hello and welcome back to BitLearn. So far we did mini series on C programming, we looked at AI models, we looked at OS design, all of which are foundational topics in computer science. So this mini series is on data structures. This is where we explore how complex software systems organize, access and manipulate data efficiently. So if you look at any real life software, there is a lot of data that has to be handled. Millions of transactions, billions of sensor readings, thousands, maybe even more of names and people information in a database. There is all sort of scale required to build sophisticated systems. And data structures allows us to manage this data. We will explore core data structures and implement them in C so you see exactly what's happening behind the scenes. Whether you are studying this formally or building your foundations from scratch, this is a great starting point to start building really complex systems. So let's begin. So in the first episode of the mini series on data structures, we're going to look at linked lists, which will kind of form the foundation for all the other data structures we'll look at. So to begin with, let's look at arrays. Very familiar, right? Arrays are often the first data structure we learn. They're simple, predictable, very efficient. You store elements in contiguous memory locations and you can access any element instantly just by using its index. So for many problems this works beautifully. It gives us structure, order, and it's very fast. But that starts to become a problem when the nature of the problem changes. So imagine a system that is constantly receiving data, like a huge to-do list. You're doing a big project and there are people adding items into the to-do list. Tasks are arriving continuously. So in such systems, the number of elements is not fixed. It grows, it shrinks, and changes unpredictably. And now the very strengths of an array begin to reveal its limitations. Because every time an array reaches its capacity, it must be resized. And that itself is a problem. That means allocating new blocks of memory and copying all the existing elements into it. Every time we insert an element in the middle, we have to shift everything that follows that. Every time we delete something, we shift elements again to fill the gap. So this whole jugglery of moving elements around to accommodate a new piece of information becomes a challenge when you are trying to do something in scale. And more importantly, the array itself does not allocate memory dynamically. So you have to come up with the number of elements you need right in the beginning. So these operations are not very efficient. They feel very unnatural for problems that we try to solve in real life. So at some point it becomes clear that there is a mismatch. Arrays kind of enforce a very rigid structure. So that leads to the next question. If data does not need to exist in one fixed contiguous block, what else can we do to make sure that we can keep growing these data elements? What if each element could exist independently and they all still remain connected as part of a sequence? So that is where linked lists come in. So instead of organizing data by position as arrays do, linked lists organize data by relationships. So in an array, an element is defined by where it sits. It's an index. So if you have an array of 10 elements, the index position tells us which element we are trying to access. But in a linked list, an element is defined by how it connects to the others. Think of it like a chain. So basically each element has its information and it points to the next node in the chain. So each node knows only two things. It knows what comes next. It has no awareness of the entire structure. But yet the entire structure emerges from very simple connections. So if you're able to go to each element, use the next pointer and go to the next element, and you do the entire traversal like that, you will get the entire chain. But each element by itself is not aware of the entire chain. So insertion is no longer about shifting elements. It becomes an act of adjusting pointers. Deletion is also no longer about collapsing all this space. It becomes an act of just bypassing a node. So we'll look into all those details as we go through this episode. So before we move into implementation, it helps to think of linked list as an abstract idea, as an abstract data type. That's what you will come across in your academics. So at this level, we are not concerned with how the structure is implemented. Instead, we focus on what it allows us to do. So a linked list should support creating a list. It should allow us to insert elements. It should allow us to delete elements, traverse the structure, search for a value, and check whether the list is empty or not. These are more or less the basic operations that any list should support. We talked about a to-do list. when you're doing a large project with multiple people and people are just inserting tasks into the to-do list. So what is it that we should support? We should support starting a list in the first place, creating a list. Then we should support inserting elements at different positions, because each person who's working on the project is going to insert his to-do item. Then we support deleting elements. Once I finish my task, I delete it. Then we support traversing the structure. I'm trying to run through the list to see what tasks are assigned to me. So I should be able to move through the structure. And I should also be able to check if a list is empty. This is very interesting. But as far as an implementation goes, we also need to know if the list is empty or how many elements are there. We need some list utility operations. So one important characteristic really stands out. Unlike arrays, linked lists do not support direct indexing. You cannot jump to the 50th element in constant time. You can traverse to that, but it's not like you can use index 50 and just reach the 50th element in the array. It doesn't work. You must start at the beginning and follow the chain node by node until you reach your destination. So this introduces a fundamental trade-off. Arrays gives us constant time access, but they are very rigid. So you have an array of 10 elements. If you know the index you want to access, you just hit the index and you'll get your element. That's it. But linked list sacrifices this direct access, but it offers more flexibility in terms of dynamic insertion, deletion, dynamic growth of the list, all of these things. It is not optimized for speed of access, but it is optimized for ease of changing and flexibility in extending or reducing the list size. So understanding these trade-offs is really essential, because data structures are not about choosing the best option. They are always about choosing the right representation for a given problem. Somewhere an array may be a perfect fit, somewhere else linked list. So that's how we choose data structures. Now let's go into how do we implement this idea in C. So if a linked list is a chain of nodes, then we must first define what a node is. What is that single piece or element that is out there? What does it hold? In C, this is very easily done using a structure. So you can create a user-defined structure called node, like what you see on the screen. You have one piece of information called data, and then you have a pointer. Basically, it's like a map or a navigation telling you where do you find the next element. A pointer, a C pointer, allows us to store the address of the next node. So that is what we have here. This is a self-referential structure. So this definition kind of allows us to have each node pointing to the next one. So each node is aware only of the information it holds, and it has a pointer to the next element in the chain. That's all it has. So to access the entire list, we use a single pointer called a head. So head is basically conceptually, it is just think of it like an arrow. You are pointing to the head or the first element in the linked list. If the head is null, then the list is empty. Otherwise, it points to the first node from which the rest of the list can be accessed. If you basically use this conceptual name called head, which is pointing to the first element, you can go to the first element in the chain, then use the next item in each of the element to go to the next element in the chain. And like that, you can basically traverse the entire chain. So nodes are created dynamically using memory allocation. Like what you see on the screen, you can use malloc, you get the size of a structure and allocate memory for that. So this dynamic allocation is what gives linked list their flexibility. So in a typical array, you predefine how many elements you are going to store. So the system will basically mark that much of memory and allocate it to the array, and now you can fill it up with the number of elements you have declared. So if you declare an array of 10 elements, the operating system or the C program will give you space to hold 10 elements of whatever is your data type, and you can fill it. But in a linked list, you start with no memory allocated to you. So it is efficient in terms of memory usage. You have to dynamically do these mallocs. You basically have to allocate memory whenever you want to create a new node, and then you also have the job of maintaining the sanity in the linked list. What do we mean by that? Once you create or malloc some information, memory, and you put your information into that, it is also the job of the person who's writing the linked list code to make sure that the pointer points to the next element in the chain. So that is how we manage a linked list. So now let's look at how the structure behaves through its core operations. We talked about an abstract data type, saying that a linked list is In abstract, it is a chain of information or elements. Let's look at what are the typical operations that we do. One of the most simplest operations we do is inserting at the beginning of the list. It's pretty simple. Initially, no memory is allocated. You have this imaginary pointer called head, which is pointing to null. There are no elements in the list. So instead of shifting elements, we simply adjust the pointers and add new nodes into the chain. So no data is moved. The structure changes by updating the relationships. Traversal, on the other hand, reflects the sequential nature of linked list. To visit each element, we start at the head, we follow each pointer until we reach the end. So no shortcuts, access is linear, we just go one by one. If you look at the piece of code out there, we have a while loop which basically points to the first element, and then you keep traversing to the next element that is stored in each of it. So deletion is where elegance really comes in, where we don't have to shift any elements, we just change the pointers. We do not remove a node, we modify the pointer of the previous node to skip over the node we want to remove. Conceptually, if you have A pointing to B and B pointing to C, we simply make A point directly to C, B is no longer part of the chain, and then we can just free that part or free that memory. So this leads us to a very important principle of linked list. Data is not moved, data is just there in different parts of memory. Relationships are moving. If you delete something, we change the pointer to point to the right element. Or if you insert something, we update the pointer to point to the new element. So it's all about relationships. Data itself is just there in memory. So if we step back, we begin to see that the linked lists are not just academic structure that you study. Their underlying idea, it kind of appears in many real world systems. So they form the basis of stacks, queues. When we implement all of these things dynamically, they're also used in hash tables, they handle collisions, a lot of things. So as we build more and more complex data structures, we'll get to see how the linked list forms the foundation of data structures. So what we have seen so far is the simplest form, the singly linked list, where direction of traversal is in one direction. But this idea can be extended further. You can have a doubly linked list where each node maintains a reference to both the next in the chain and also the previous node in the chain. This allows us for traversal in both directions. So in a circular linked list, the last node points back to the first, forming a loop that supports continuous iterations. So it's pretty flexible, so you understand the concept of a linked list, and then you can start building much more complex data structures, like a doubly linked list, which will allow us to traverse in both directions. A circular linked list, it's more like a circular buffer where you run out of elements, you overwrite the last one. So a lot of advanced implementations can be done with one basic simple concept called as a linked list. So now let's look at when do we use linked lists. They are most effective when the size of the data is dynamic, when insertions and deletions are very frequent, and when sequential access is quite enough for us, then it is most suitable. They are not that suitable when we need fast random access. So when memory overhead must be minimized and when performance is very critical, that's when linked list may not be the best one to use. So choosing between arrays and linked list is not about having a preference for one, it is about aligning it with the right problem. So that brings us to the core takeaway of this simple episode on linked list. Arrays are about where data is. You have an index, you know at which location the data lives. Linked lists are about how the data elements are connected to each other. So this shift from position to relationships is one of the most important ideas in data structures. So once you understand it, you begin to see that data is not just about values, but it's also about how they are interconnected. So in the next episode, we will start building on this idea and construct stacks, queues, and we will go on to the other abstract concepts. So meanwhile, keep learning. Make sure you grab an academic book to make sure that you get these concepts well. So this is BitLearn. Come back for the next episode. Until then, drop some comments, do subscribe to this episode, like this video. See you soon.